request all audience members to kindly keep their microphone muted, and I will quickly formally introduce Professor Alex. Of course, if you work in the power electronics area, you clearly know about him. He's an extremely distinguished academician and researcher. But I have his formal bio with me, and so I'll quickly read that out. So, Professor Alex Wang received his BS degree from Zhejiang University, China in 1983, and his MS from Chengdu Institute of Radio Engineering, China in 1986, both in EE. He received his PhD from Cambridge in 1992, was a professor at CPS Virginia Tech from 1994 to 2004. And from 2004 to 17, he was a Progress Energy Distinguished Professor of Electrical and Computer Engineering at NC State, where he established the very famous NSF Freedom System Center and the DOE Power America Institute. Since 2017, he has become the Dula D. Cockrell Centennial Chair of Engineering at University of Texas, Austin, where he directs the Semiconductor Power Electronics Center, SPEC. He has mentored and graduated more than 100 PhD and master students, has published more than 700 papers in national conferences and journals, has been granted more than 20 US patents. He is a recipient of the NSF Career Award, the prestigious R&D 100 Award, the MIT Technology Review's 2011 Technology of the Year Award, the 2019 IEEE's Gerald Killman Innovator Award, the 2020 IEEE Pell's R. David Millbrook Achievement Award, and the 2021 IEEE PES Energy Internet Pioneer Award. He is a fellow of IEEE and National Academy of Inventors. So as you can see, I mean, he's almost won everything that is there in power engineering and power electronics. These are all the some of the best accolades and prestigious. And he's one of the pioneers in the topic of solid state transformers, for which he has kindly agreed to give this lecture. So thank you again, Professor Huang, for accepting this invitation. And we're very, very glad to listen to you. Thank you. Over to you.
Thank you. Thank you very much. Good evening, everyone, and thank you for having me to talk virtually about some of my work. Yeah, I work in the area of power semiconductor devices and the power electronics. So today's topic is more power electronics topic. So we will see if some other time I can also talk a little bit about the semiconductor device aspect. But everything, of course, tied to semiconductor end of the day. So that's why the name solid state started. So today is really more highlight a little bit more the journey of developing the solid state transformer in my group and give a quick example of several implementation. As you can see, what's common to all these implementation is what kind of semiconductor devices are used. And so that's one of the key technology. You will walk away with some idea on where we're heading. I think Sanajo mentioned that I was at NC State many years ago. So really the work on solid state transfer really started in about 2007. So we basically, look at the power electronics technology and the impact to the humanity and the society. We basically electrified our low voltage system. Low voltage, I mean by 400 volt and below system with solid state technology. So today, almost everywhere you go, those are solid state technologies. You can call iPhone charger a solid state transformer if you want to. Of course, by definition here, we're talking about medium voltage solid state transformer. So in all those low voltage application, it's already electrified with solid state devices. That started almost in the 1970s when we invented and developed power transistors, right? So can handle voltage in a couple hundred volt range. So 2007 was the time we proposed to the government to establish the Center for Excellence, the Freedom System Center. This picture basically shows what that freedom system concept means. We think this is a way the future power delivery and management system should look like, where the 60 hertz transformer, which is showing on the right-hand side, should be replaced by a solid-state transformer showing on the left, that really interface between the low voltage system and to the medium voltage system. So the center actually focused on two technology. One is solid-state transformer, coupled with the software. Really, you can position this as an energy router, exchange power, and provide ancillary services to the electric grid, right? So, and of course, on the low voltage side, it's not only the legacy AC, but more importantly, is support the DC microgrid, like everything showing here, energy storage, PV, will be DC based. Another technology we developed at that time is called, it's basically a solid state circuit breaker, but because the system fault current is going to be very, very low in the future because you have solid state transformer. Here, then this fault current will be limited. And this is more like an isolation device or like a contactor, but it need to be very, very fast. So we give it a new name called fault isolation device. It's not as a well-known acronym we created at that time, but solid state transformer is the one most people call this. Um, so there is, of course, a global interest since then to develop solid-state transformer technology. As you can see, this is just a publication since that time. You see rapid publication worldwide, and you go to a conference everywhere. You have a session on solid-state transformer. So, of course, the interest uh, drive this kind of interest is really everybody sees this as a future of modernize the grid at least the edge of the grid, which we mean by medium voltage means several thousand volt to sub transmission system like 69 kV in the United States. So that's, but moving to today, people's views change a little bit. When we started doing this, we focused on distribution grid with a residential customer as a major focus. But fast forward, the need to decarbonization the society at a utility scale, there are a lot more interest at a utility scale to use solid state transformer. So on the bottom left hand side here shows this utility scale solid state transformer application example, which you still have this legacy AC grid. This is the legacy AC grid, but we have this emerging generation of energy resources. They are all DC technology. So then you need a solid state transformer. In this case, solid transformer we need is a DC to AC solid state transformer instead of just AC to AC, which was originally envisioned when we start doing our work. And the data center is also moving towards DC data center. So you can think data center is become a major DC load of the future. Again, solid state transformer has a major use case here. So this is today. Today, we think this will be a short-term application space. Moving forward, long term, you will move towards a more what we call the DC based to a grid, where you even the high voltage system is also solid state transformer. So we actually are currently working on a DOE proposal to develop this ultra high voltage solid state transformer that eventually will support several hundred thousand volt kind of application. So that's a more long term. Once you have that, then of course there is no in here you only need a DC solid state transformer, which from a technology point of view actually is a little bit more easy. You only have a DC to DC converter. But the challenge is the isolation voltage required here become very, very high. So this is the vision of the future when you start to move the whole grid towards solid state. So what exactly is a solid state transformer? My definition is it has to be a medium voltage power converter with isolation. This is just typically the use case that you have to have a galvanic isolation. So it depends on whether you have input is AC or output is also AC, or we can define this as type A. Like reason, meaning this is one type of solid state transformer. If you have a AC, then you have an intermediate DC, then you can define A, B, C, D. So most people working on the so-called type D, where they have multiple stage of power conversion as well. So this is some simple classification and definition of the solid state transformer. Um, so the one challenge is typically the AC side is very high voltage. So here we showed everything AC, right? Because this is legacy AC is medium voltage, it's very high voltage. So semiconductor technology does not support very high voltage at the moment, although that's one way we want to go to. Then one way to do it is put several of these converter in series, because you have this galvanic isolation, so you can put them in series, put them in parallel. It does not violate any of the circuit connection constraints, so you can do it. So input series, output parallel is one of the very popular way to increase the voltage on the medium voltage grid side. So the technology really that important is semiconductor devices, topology, of course, as well as this transformer called medium frequency transformer. Why we don't call them high frequency, I will show you example. So again, if it's AC to DC, you can completely get rid of this AC, just keep the DC side on the low voltage. AC side is still AC. But if you go to the future, I mean, then you only have typically then a single stage is all you need. Become much more simpler from semiconductor and cost point of view. This will reduce the cost. One technology behind is semiconductor. So many of you know that are working in this space. And also I start my career working on semiconductor devices. So the first device I work on is really silicon MOSFET and silicon IGBT in early 80s. So until today I have some project in this space and some project in this space. So I classify this as several wave of technology, with wide bandgap technology sitting here, the third wave of innovation. What is the fourth wave? Not clear at the moment. Maybe ultra wide bandgap technology, maybe not. But anyway, so these are the devices already commercially available here. So that's one of the major driver. What separate these devices is they're getting faster speed compared with silicon technology. So in terms of implementation, one of the first example I want to show is utilize the silicon carbide devices with very high breakdown voltage, 15 kV. This is not commercially available devices. It has been made available to us through research collaboration with, at that time it's called Cree. So we customize the design and increase the breakdown voltage to 15,000 volt. So it's still one of the highest breakdown voltage devices that was produced for laboratory use. The major takeaway is why we want to go to this device is higher voltage, everybody understand, but we also need to talk about frequency. Higher voltage and higher frequency is important for solid state transformer. It's not important for application like HVDC, MMC, where you don't really need to switch at a very high frequency. The reason is we have this galvanic isolated transformer, and transformer directly scale in terms of size as voltage times frequency. So this number need to be large to make the transformer smaller. So compared with silicon technology, really, if you want to compare at the higher voltage, only device available are silicon IGBT and some other bipolar devices are relatively slow. So their figure of merit in terms of voltage time frequency is a couple hundred times smaller. Here, of course, this is a more sustainable figure of merit that not only take advantage of the higher switching speed, but also take advantage of the soft switching capability of isolated topology, which is much easier to achieve soft switching because the magnetic component than a traditional inverter, like a voltage source inverter. So this is the device we tested at that time, showing very high device figure of merit. So this device was the one we used to implement one of our first solid state transformer, one of the first, not all of them. The topology we use is a resonant topology here. So there are only two devices on each side. So there are in total only 4 devices. These are very tiny little devices with on resist in the range of 100 milliohm or higher. So it's not a very high power, high current device, but it's a high voltage. And this topology directly convert rectified sine wave. In this case, the power flow only go one direction because there is a diode here. And then since it's a resonant converter, it will copy the half sine to the low voltage side. So this is a 7.2 kV, and this is a couple hundred volt. Then you can use another on a low voltage silicon device to get a full sine wave. So this is basically a type A kind of topology. The first one I showed, classification is called type A kind of solid state transformer. So this is the easiest way to get an AC to AC solid state transformer. And the devices is shown here. You can see this is a very early stage of packaging. Using this kind of a non-standard packaging for testing. From a device point of view, since the device voltage is so high, even the R-on is so high as well. As you can see, our R-on is actually it's much higher than what I mentioned. Actually, it's close to 1 to 2 ohm. But even that, you can still get a substantial output power because the current you only need a few amp to get very high current. Important thing is device voltage utilization, right? So if you can increase the voltage, and the same power will mean much less current. This is the optimization chart to show the utilization of the devices. What is changing is the switching frequency, which is the resonant frequency we talk about. And you can see this potentially can operate at the 20 to 25 kilowatt level. The semiconductor you have here is only 2 very small 15 kV devices. So long term, this kind of solution is very attractive if we can commercialize this. So as we speak, we are actually still working with Wolfspeed to try to commercialize this kind of devices at 10 to 15 kV level. So this is actually the hardware realized there, and then you will not be able to see too much. The semiconductor device, silicon carbide is really here. Only these two are high voltage silicon carbide devices. And this is just outside of that enclosure. The test the efficiency was a world record at that time. If you look at the top one, achieve almost close to 98% efficiency. So of course, this is one area when people look at solid state transformer is can you be cost effective is one question. The other question is can you be as efficient as 60 hertz? I think the efficiency can be designed to be close to 99% these days. If we do this again, probably we can go up to 99%. So efficiency is really matching the line frequency transformer. Cost is still a major challenge, so we're probably going to that's why I think you require commercialization to drive down the cost. So this is one type of solution, is a direct medium voltage implementation. You need very, very high voltage devices. So what I showed you is just a 2-level topology. Using 15 kV device, 2-level topology is already sufficient for the distribution grid in the United States, which is 7.2 kV single phase. But if we need go even higher voltage, then you can use maybe 3 levels, so you don't need too many converter stages. Another quick example of more recent work is this device can also be raised by putting a lot of devices in series, which is very straightforward concept. So again, we showed a similar topology where we have a resonant converter here. On the AC side is showing on the right-hand side. In this case, just we need a high voltage AC switch, which can be realized by two MOSFET in back-to-back configuration. Then you can connect AC voltage. So one problem with AC grid is they have positive and negative polarity. So you always need more devices to handle the positive and negative voltage of the AC grid. So here shows the minimum number of devices, 4 devices, two of them used to form an AC switch. So on this side is basically another half sign you can generate here, but you can control this half sign by having another buck converter. For example, this could be a PV. So this one could be a PV inverter, basic power go from the PV to the medium voltage grid. You need 3 of these for a 3-phase system. And this is a single phase picture. So this topology is simply, this device can be realized with device in series. So so we did a lot of research, look at other people's work. There are many people look at device series connection. You know, even in silicon days, you can look at silicon IGBT. But one simple message is device like silicon carbide MOSFET is much faster, so it's much easier to achieve series connection. So this is against the conventional wisdom, right? The faster you think voltage balancing is harder, in reality, actually, it's easier. Um, so we put 10 of these devices together. Each one is 1700 volts. So the achieved voltage is actually 17 kV. These are device utilization, meaning what is the actual voltage, how much derating you have, and so on and so forth. So so there are many techniques to balance the volt. The key issue is balancing the voltage. Um, and then we use a very simple method we call the RC snapper to achieve this kind of performance. And the power density is a difficult one to measure. Some paper don't have it. This is the size of the density. Yeah, the key issue I mentioned is really when you put a lot of devices in series. In this case, we put 10 of these devices in series. So how about the voltage balancing? So one of the easy one is just use a simple RC slumper. In this case, just a C slumper. R is for static balancing. With this is really very simple to implement. So the performance looks pretty good. If you look here, the voltage balancing almost perfect across all these 10 devices. So this is test at 10,000 volt. This is a picture of the device. Because you're using device series connection, this device look very, very big. So the dimension is showing here. This device actually has 20 devices, right? Because you need 10 of them in one direction, you need 10 of them in the other direction. So you have AC switch. Altogether, you need about 40 devices in this converter to implement this. So this is the final specification. The power rating is around 100 kW. So this is the more powerful single-phase solid-state transformer. Here is the hardware under test. So so this is a perfect kind of rating for like a string inverter, like a PV inverter application. This is how we did the test, and there is the transformer here. It shows the transformer has a turns ratio about 7:1, and this is a waveform because the resonant converter, so you get pretty nice current waveform on the grid side. And so this is the resonant, this is transformer current. Efficiency, this one is measured in a very, not a standard way, but the 50 kilowatt is about 96% efficient. So this data point is probably more useful than this one, as shown by this statement here. The student basically tests this by increasing the input voltage. So in real world, of course, you should not test this way. You should test, just change the load, not change the voltage. So this is another way you can get to a medium voltage solid state transformer. Uh, the last example I want to really highlight, of course, is a higher power solid state transformer or three-phase one. Um, the as I mentioned, there are a lot of worldwide interest in this, right? The power level is getting higher and higher, and as you can see, there are several examples showing here in the megawatt range. Then what kind of configuration, type A, B, C, D, I mentioned, what kind of topology is summarized here. So in our case, we're using type D topology, meaning it's a two-stage solution, and then the device uses 1700 volt. In this case, in, to reach higher voltage, you use the so-called modular architecture. The DC side, this is a DC to AC solid state transformer. So the DC side is for 1500 volt renewable energy system. Here is the picture of the developed hardware. And we also call this M4 inverter. Basically, it can connect to a 4160 grid. It has PV and storage. So this is called multi-port, medium voltage, multifunction um, uh, um, converter, basically. So the topology used in this case, we have to put several converters in series instead of device series. Use converter in series. The principle of this is pretty straightforward, right? Your input, your AC side is in series as shown here, and DC side you put them in parallel. So then you can generate a higher voltage at the output side. So this is currently most high power SST use this kind of architecture. The disadvantage of this kind of solution is it's very complex. You have many converter, as you can see here, many here. Um, this is another picture here. This is same picture showing the enclosure, and this one shows what's inside. And you can see we have total of nine modules, nine modular converter. Basically, each one is a high power converter. Then you have three in each phase, B phase, A phase, and C phase. And this is the other side of the picture. And this one that you saw the magnet. This is the magnetics, and this is you see mostly the semiconductor side. So to test this, of course, is also difficult. So long this is how we did the test, and here is basically you circulate the power. Your AC grid come in, you go to and you get the DC, then you go back. So the power is circulating between themselves. So you don't need a very high power load. And this was tested at about a third of the power, demonstrate about 98% of the efficiency in this solution. The each of this modular converter really use this kind of topology. There you have a DC to DC converter, then you have a DC to AC. The DC to AC here, we use the so-called dual active bridge. Dual active bridge is actually an isolated buck boost converter, basically, right? So your output voltage can be higher, lower than the input. So therefore, you can, if you go to extreme, you can go to zero. Therefore, you can directly generate a half sign. So this is one way you can do is you can generate directly from DC to a half sign. And therefore, you already got the DC to AC, but then you need to get the full sign. You need this operating at 60 hertz. You can another way you can do is directly go from DC to DC, then operate this as the inverter. Then that way you get the traditional three-stage solution or two-stage solution. We have additional batteries through about boost converters here. So this is some of the topology considering each module is about 110 kilowatt. One of the key thing about this dual active bridge is how to ensure its soft switching capability. Even though silicon carbide is very efficient, but we still want them to be soft switching to improve the efficiency. So silicon carbide is fast, but it's not lossless. So we still need to try to achieve soft switching in this kind of topology. Um, this is a picture of that one of the modules. This is primary side. I think this primary side, secondary side, and this is the magnetic. Magnetic includes inductor, capacitor, and a transformer. This is a transformer. This converter operates at a DC-DC converter mode, uh, achieve very high efficiency, uh, more than 99% efficient is measured here. In DC-AC mode, efficiency is lower because the output voltage change from 0 to a very large value. About 90, the highest one is about 97.49, 97.5% efficient. So this is at the module level. Power density achieved is here. So one of the key solution here, of course, is silicon carbide power module. In this case, we use a 1700 volt power module. And since it's a module, the footprint become bigger. One of the major issues is how to design a bus bar to connect all the devices together. So the typical solution is a laminated bus bar or printed circuit board-based bus bar. Printed circuit-based or PCB-based bus bar typically not used for very high power. So this is one of the attempt to look at a lower cost solution to use a PCB-based bus bar for high power application. And it worked very well. And actually, PCB-based bus has an advantage to allow very easy optimization of the loop. So here we showed basically two loops. Loop one is between drain to source of the devices. And then because you need a larger DC link capacitor, which sit a little bit far away, so you have another loop. So the typically in IGBT, you only have loop two, you don't have loop one, because IGBT is much slower, so you don't need this capacitor here. So for silicon carbide, the speed is so fast, you need local decoupling of the high frequency a loop. This is a high frequency loop with additional capacitor. So this is another way to show in the circuit way is you have semiconductor devices here and how to decouple this high frequency current is here. So once you come to here, become low frequency. So this capacitor is important to minimize the voltage overshoot. So we have achieved a very good voltage overshoot containment under even very high current, 250 and only about 100 volt overshoot. And there is some resonant oscillation between these two loops. So this is an important issue in any silicon carbide high power converter is look at this loop decoupling issue. Another issue I mentioned is how do you do your control of the converter to achieve soft switching? So this is a topology dependent, and it is load range dependent. So if you're operating in very narrow, typically narrow load range, narrow voltage range, it's a little bit easier. If we operate in a very wide range, it becomes much harder. So, but anyway, so one technique we find out the turn-off loss is still substantial in this kind of devices. So one standard technique you can do is slightly increase the output capacitance of the transistor by parallel additional capacitor, which is well known as a snubber capacitor. So it shows a few percent improvement in the efficiency by using a smaller capacitor. So that's good. So soft switching basically typically solve the turn on loss, but turn off loss is still a problem. Particularly like a DAB can have a very high turn off current. So that's a disadvantage of DAB, particular DAB operating in a very wide voltage range. Another key technology that I want to very quickly show is as we go to higher and higher power, we need a higher and higher power transformer. And these are called medium frequency transformer. It's medium frequency because the frequency we're dealing with typically is not super high. it can be much lower than 100 kilohertz. So basically from 100 kilohertz to about 1 kilohertz range. And this will show several different design, look at different material, different shape. And this is the one we use in this 1 megawatt converter. Use a nanocrystal material operating at 15 kilohertz. One of the key challenge, of course, is the insulation. So this one is one of the key challenge. So the major electrically, you need to design this for high efficiency. Thermally, how to cool the losses in the transformer. This is a 200 kilowatt, so even 1% of losses is 2 kilowatt. That's a lot. So efficiency has to be extremely high. In this case, we achieve 99.85% efficient. In this transformer, and then insulation is the third challenge. So basically, you have electrical, you have thermal, and you have insulation challenge. So to me, these are the bottlenecks to some of the SST from a technical point of view. And then the remaining one really is the cost and reliability. Many people think just go to higher frequency is good, but because these three major things are limiting you. You need high efficiency, you need good remove the heat, and you need to have high insulation. So your design is really constrained. This is a sample of all the published medium frequency transform at that time. This is about 2 years ago. You look at a frequency go higher doesn't mean the density is higher. It doesn't really show a clear scaling. You want to say something like this, it doesn't really happen. So this is yet depend. Also, you have different materials, therefore it's not apple to apple. It's more like apple orange pear and different kind of thing. Air means the core is air core. You can even build transformer with no core. So this is remain an interesting research direction to have no core, very high power transformer. This is our group, several examples of our group's work with different kind of frequency, but for most of the reason the frequency is changing is we're using different kind of material. This is nanocrystal, and these are more ferrite-based solutions. And this is the one that we used in this 1 megawatt converter. And this solid state, this is medium frequency transformer. Use a very good core. It's a nanocrystal core, and with very high saturation flux. And the actual picture with going to the converter is here. This is the silicon carbide converter we use with this to form this module. This transformer efficiency is really very high. This is the converter efficiency is the blue that include all the semiconductor. This is tested in the DC-DC mode. Okay, go from a fixed voltage to another fixed voltage. I think it's a 1300 volt. This is a test at a 1300 volt because the device is 17. And the transformer efficiency is 99.8, as I mentioned. And these are the lateral convection cooling picture, meaning the devices remain relatively cool here. So basically, this is another key technology you have to develop and reliably to support solid state transformer. The insulation is the one that's most difficult among all this. In order to keep a partial discharge free operation, depending on which grid voltage you're going to connect this to, the higher you go, the more challenging to design the insulation layer. So in this example, this is an unported transformer with a special design bobbin to keep the insulation voltage high. So this is there are many things going on here to how to improve the insulation voltage while keep this compact. Right, compactness is fighting with increasing the insulation. So power electronic doesn't scale basically in this reason, right? You make everything more smaller, your voltage is still high voltage, then and your insulation become more challenging. So this is where I think one of the remaining challenge here. With that, I want to stop here and see if we have a few minutes to see if anybody has any question.
Thank you, Professor Alex. Excellent exposition of all that your group has been doing in this area
Mm,
for such a long time. It was fascinating to see some of that. I have several questions myself, but I'll first see if the audience. Yeah, maybe can I request you to please type in your questions in the chat box? That will be, I think, quicker way to do, and I can read it out. So if you have any questions, please type it out in the chat box.
let me see if I
Uh,
can check.
Maybe I can start with one question myself, Professor Alex. You started with the very high voltage 15 kV device, two level, and then you show the modular structures, right? So
Yeah.
generally, if there is a this let's say kV level, yeah, converter design problem, where do you think the technology and what are the sort of the arguments in favor and against going with a two level truly high voltage device versus making something modular and series connected?
Yeah, I think modular is two reasons modular is popular. One is availability of the devices. The other is you can potentially achieve multi-level waveform.
Mm,
So that will make your AC side current waveform better. So this is if you have a very high voltage device,
mm,
and you will need to figure out how to handle you keep the current harmonic really low, right? So in that case, a simple two level, you may end up with a very large filter. The downside is really just you need a very large filter on the grid side. But this argument, of course, doesn't apply if we go to DC to DC
mm,
converter level, then because you have a capacitor, so you have a stiff DC voltage. It does means the transformer will see a higher and higher dVdt. So
right.
transformer insulation need to be tested uh, under higher common mode voltage is still the same. If it's a 10 kV system, the overall common mode voltage doesn't change, but the dVdt per transformer will change. So there are a lot of this tiny little thing that point to, hey, maybe we don't really need very, very high voltage devices.
Mm,
I think the history, of course, will tell eventually we'll move to higher and higher voltage. And it will be a little bit slower, but as you can already say, it's already happening, right? So
mm,
not just for solid state transformer, right? There are other applications as well, right? So people are today commercially can get 3.3 kV, 4.5 kV is also, I think some company claim they already have. So I think it's still going to go to 10 kV, but you have to be it's not like you just drop you in the topology so simple uh, job is done. Yeah, you have to look at some of these issues here. Like I talk about mostly insulation and the filter, and whether you can switch fast enough to keep the filter small. So, like the one we showed at the first example, that we operate that as 40 kilohertz. The reason we can do that is because we operate in the resonant mode.
mm,
Resonant. So that's pretty high frequency. So at 40 kilohertz, at a couple thousand volt, yeah, okay, the filter probably is doable. Yeah, doable. And so those are something. I think, of course, another reason obviously is the market. Can high voltage serve multiple market? If
mm,
nobody's going to probably develop this just for SST, unless SST market is already very big. So again, maybe the end of the day is you start with many modular design. You create the market, you create the enough incentive for people to say as long as you can show you cost effectiveness I
mm.
think the manufacturer may have a motivation to do so, yes.
Yeah, yeah, that definitely makes sense. So I'll now read out some audience questions. So one question is, what is the diode you are using in this converter for dead time conduction? And what is the present status of, you can read it yourself maybe in the chat box.
Yes, yes.
What is the present status of staking fault defect in the inherent body diode in this high voltage diodes? Um,
That's that's an excellent question. In the first example we showed you, that's a really early stage, a little bit early stage of the silicon carbide work, and the dial is really bad. So we have to block the dial. So I
mm,
didn't talk about that. So in the first implementation, the body dial is not used. We have a Schottky dial blocking it,
mm,
and then we parallel a separate high voltage dial, a JBS
mm.
dial to it. Fast forward to today, most manufacturer we talk to recommend to use the body dial, and they think it's no problem for short duration conduction. And so in order this converter, of course, the body dial only conduct like I think um, the question asked is really during the dead time. So
Mm.
the last example you saw, it has a body dial. We use a body dial. And the second example, the one in series connection, is also body dial is used. So this one, of course, is about manufacturer dependent question. To look at whether the basal plane defect issue has gone away. Most manufacturer said they solved this problem.
Okay, okay. S- the same person has some other questions. Said that the R-on of the devices seems high. I think in one slide you showed it was about an ohm or so. So are these non-punch through type devices? What are the type of devices
Oh,
technology?
okay. So the first example shows a very high on device.
Mm,
That is a very relatively small die, and it is a 15 kV wafer. So the epi wafer is really thick, and I don't know. This is the MOSFET. So I don't know exactly whether the thickness. The thickness probably is 120 micron at that time.
okay.
Around 100. I don't know if it's a long know exact whether it operates under punch-through condition or not, but
Mhm.
probably it doesn't matter too much. It's just a MOSFET with very small die at 15 kV. There is nothing you can do about it. It's just a piece of resistor fundamental. So the only way to improve that are on this is not IGBT, right? So this is just a MOSFET. So therefore, only way you can do is make sure you use more device in parallel to get higher. So it's basically channel mobility, all these things really doesn't matter at that voltage level too much. It's majority of the resistance is coming from that epi layer. So.
Okay. And another question from that person is in the series connected architecture, what is the DVDT across the entire bridge? Yes. Is there an inherent DVDT immunity that you're using so that you are not protecting against the internal BJT turn on?
Oh, okay. So, oh, interesting. Okay, so the DVDT, I think I showed one waveform with a very nice voltage sharing. That one has the DVDT information. I think it's this one. If I move this one here,
Hmm.
yeah, this one shows the DVDT here. So this is a turn off DVDT. This is a turn on DVDT. So, yeah, so really it becomes slower because remember we put a snubber capacitor across this solution. We put some capacitor here. So the
Right.
DVD is slower, but the reason we make it slower is not necessarily worry about the BGT.
Hmm.
Uh, the BGT turn on in silicon carbide really doesn't happen for a couple of reasons. One is the turn on voltage in silicon carbide is 3 volt compared with silicon. So the BGT is very hard to turn on in silicon carbide. The second thing is, so that's a inherent physics, right? So you need more than 3 volt to turn on a PN junction. The second is the PN junction is so bad, and so there are other things helping you. So we hardly you see anybody reporting bipolar transistor turn on in silicon carbide. So obviously this is a slower DVDT. we have many other work with very high DVGT, close to 100 kilovolt per microsecond. We don't say IGBT, we don't say the BGT turn on issue. So I don't think you can easily turn on just by calculation to how much current you need to turn on a 3-volt PN junction. Yeah. So
Right.
that probably the first order thing that helps this bipolar parasitic bipolar effect. Yeah.
And on this picture itself, Professor,
Yeah.
this devices that you put in series, you are using discrete packaged devices and
Yes,
you're connecting them on a PCB, right?
they're discrete. No, they're not. They're connected. They each has their own individual heatsink, and there is a bus bar connecting them. Yes,
I see.
so they are isolated from a heatsink point of view, because you need to flow to the heatsink.
Okay.
Yes, those
So
are discrete devices in series. Yes,
they have
so
all separate heat sinks of their own, which are
yeah,
isolated.
each one has a separate heatsink because otherwise you have the package is only 1700-volt package.
Mm,
It doesn't have an isolated substrate.
mm,
So that's another thing that has to be carefully considered whether you want isolated substrate doesn't work if you put all of them in series. So you better not have them. So
mm.
to reduce your thermal resistance. So yes. So
Right.
it's a standard commercially available 1700-volt device.
Mm,
Each one, I can't remember the R on, but of course, once you put all of them together, of course, the R on is pretty high. But you
mm,
also have a very large space to dissipate the heat. So
mm,
so it's bigger. So it can be done. I mean, this is so if you are not really worried about space, you can put one of this module together. And if you look at the cost, of course, this one cost is very good compared if someone is selling a 15 kV silicon carbide module today will be very expensive, right? That's again
mm,
why you
mm,
don't see them is they are very expensive.
mm,
It's
mm.
just difficult to make them. The epi is too thick, right?
Right. Right. So would you say this is sort of scalable in the sense that if you have been able to do it for, let's say, 10 devices in series, this approach, you would say is scalable in terms of voltage going up?
Yes, I don't think there is anything stopping this part. Yes, I think we can keep going. This
Okay.
is not the limit. It's just a little bit bigger, right? So
Mhm.
yeah, this one so it's really easy to I would think it's relatively easy to do actually. Yeah.
Okay. Okay.
We have other work, as you know, we have a Cascode
Yeah.
solution as
Yeah.
well,
Yeah.
which I didn't talk about here.
Yeah.
Which this one you need driver. We need 20 drivers.
Mm.
You can see all this little white thing here on the
The
top.
ports. Yeah.
These are isolated power supply. So
Mhm.
the devil is in the detail. Basically, once you have all the devices, each device need a driver. Each driver need a power supply.
Mm.
Those costs become a substantial part of the overall cost, actually. Yeah.
Mm, mm, mm. Okay. Okay.
So Casco, of course, removed some of those, but
Mm.
also has some of the other challenge. For example, voltage balancing is not as good as this. Yeah. Yeah.
Okay. Okay.
So
Understood.
so
Yeah.
we have a Casco device that also can reach this voltage level. Yeah.
Yeah. Yeah. Yeah. I know. I think we call it the super cascode or
Yeah,
something
super
like that, right?
Casco. Yeah.
Yeah. Okay. Next question is for the EMI filter, how do you select the core and frequency of operation? Should be designed for fundamental or high frequencies? Uh,
I think this part will be similar. We haven't spent too much time really looking into that,
mm,
but it will be similar approach to design EMI filter. Mostly you will be looking at a higher frequency EMI filter.
mm,
Yeah, looking at your switching harmonics and higher. Yeah, fundamental of course is your filter design. You take care of your filter design to meet IEEE uh, 1547, that kind of standard requirement.
mhm.
519, a couple of standard governing that. So yeah, EMI, but it is true, medium voltage EMI standard is not there. So you probably just have to look at apply some low voltage power supply standard to this. So overall, there is a lack of established standard for solid state transformer. In the installation, we copy something from 60 hertz transformer. EMI, there is nothing. Okay, we just look at the power supply. But does the utility grid really have that requirement? Not so sure. But
So do you think that's an interesting point that you raised? Do you think there needs to be some sort of international standards on this SST technology to come up with what should be the requirements and stipulations and safety requirements, for example?
yeah, there is some effort going on. There is a working group, but not
Mm,
there no standard has been issued yet. So I'm
okay.
involved in one of the IEEE, but there is also IEC group. So there is some working group currently looking at this, but the way they look at it is they'll still look at right now it's just some working group recommendation, and so. But for example, insulation will be one of the most important one out of all this. That is still being discussed on how this should be tested and rated, right? So like
Mm-hmm.
how do you do BIL tests on this kind of thing?
Mm,
And so this one has to pass a BIL some uh if as soon as you say transformer, they think this is transformer, they need to test down the BIL. So better way to call this is not call them a transformer. So
mm.
that's
Okay.
unfortunate. Yeah.
Yeah. Okay. I think the next one is a more general question. Is there a trend that conventional distribution and transmission transformers are going to be replaced by SSTs in the near future? What do you think?
Conventional trend in the conventional distribution. Okay, so again, I said we start with our vision is very broad. We say we're going to replace all distribution transformer and substation transformer. Now my prediction that is going to be a second phase and third phase of the SST commercialization. SST now no longer need to immediately address that. Because that one, I think the number one challenge is cost.
Mm,
That one you have to, because the functionality in those applications probably is not as interesting as the other one. So then you have to come down as a very low cost and very high reliability, which is always harder when you're at the beginning of your scaling, right? So right now at the beginning of the scaling, so therefore we need to look for our EV adoption kind of example. Do you go to luxury car or you go to passenger car for
mm,
everybody? So
mm,
most company chose to go to the luxury car segment for this reason. But
mm,
so so for us, our luxury segment for SST is large scale electrification, renewable energy integration, electric vehicle charging infrastructure, AI data center. In those cases, then like I said, the word transformer is misrepresenting. We are providing DC as a service, direct current service to all those electrification needs. In that case, 60 hertz transfer just don't can't do it, right? So they still
mm,
have to the 60 hertz transfer plus an inverter to do what we can do, right? So therefore, you will come in at a little bit more competitively. You will become more competitive in those space, and also many of those applications are space constrained. So you come in at use much less land, less material. But
mm,
less material here means copper and steel, and less weight. So all this we win. Okay, we win on the weight, we win on the material consumption. So at the end of the day, long term, then the cost come down. Then we can tackle the distribution transformer, a single phase because the distribution many of them are very small, smaller, tens of kilowatt. The smaller, it's like a passenger car, right? So it's the same question. The smaller than your unit cost per kilowatt become, it's difficult to come down. So
right.
so at a megawatt level, we're more currently we're already competitive, I think. So long term, then the cost will come down further. So I think yes, long term. So we start with Freedom System Center is more distribution, replacement kind of aging. I think that will take, in my view, will take a little bit longer time now. So right now, our focus is more on electrification and renewable energy integration.
Okay, so we're past the 1 hour, so maybe we'll just take two or three more final questions, Professor Alex. So one thing I wanted to ask you is, I saw some in some places you were using the series resonant topology, and some places there was a DAB. So what is
Yes.
your view on those? Like, how does one go about selecting either one of those for a given?
That's definitely the classic thing. We start with a lot of work on DAB. Lately, we start doing more on resonant. On efficiency, resonant converter win. A resonant converter, the disadvantage typically is they they don't like larger output voltage range. So if you can figure out that, then you should be that's your preferred topology. One of the things I mentioned is DABs can sometimes have very high turn-off loss, and you can lose ZVS. Turn-off loss, high turn-off current, then you have more turn-off loss. Then you can also lose ZVS. So um, it's a use case dependent, depending on whether you use two stage and one stage. If you have two stage, you can use the other stage to handle your voltage variation. Then you can keep the isolation stage simple, because isolation stage is a difficult one. Yeah, difficult one. Yeah.
Okay,
So I think it's not easy to directly there, but many people like DAB. We like it. We use single phase shift, dual phase shift. We use triple phase shift in
yeah,
our control. So its control become more complex, right? You have to
yeah.
be much better. Resonant converter, you typically don't want to do too much control to it. Yeah, yeah.
Right, right. There was one question, in fact, if you see on the chat box related to DAB modulation only. So it says that the DAB, I think one of the DABs you showed was dual phase shift modulated. So I think his question is, wouldn't triple phase shift be for, especially for buck mode, would be more feasible? But I guess what you said, it's more complex. So in that sense,
Yeah, it's very complex. We have people using triple phase shift. You need to be almost it will difficult to come up with optimum design that maximize the efficiency. So the key is still you want to maximize the efficiency. So you need to do a lot of offline calculation, and maybe putting you have to have a lookup table, and how you implement the lookup table in your digital controller is a challenge. So it's a trade-off there. And so there are both are very suitable for SSD, and DAB has more controllable capability than one is the current source, one is voltage. So you can think this way maybe um, that kind of application here. So.
yeah.
So I
Okay.
think yes, you can use different kind of phase shifter modulation. So yeah, in DAB you have to talk more about phase shift and modulation. In resonant converter, you don't necessarily need to have too much of those
Yeah.
discussion. It's so simple. Yeah.
So maybe take the final question. I think it says is a modular matrix-based topologies. I think is referring to the back-to-back single-stage architecture that you showed. So, what about those topologies in SSDs as opposed to the unfolder-based architecture? Maybe I think.
Using the AC switch,
Yeah, I think that's what is being asked. I think matrix-based probably use. Yeah.
they're equivalent actually. There is nothing really different from them. You still need the same number of devices.
Mhm.
So end of the day, I think many of these different. The only thing that will change that statement is you have a true AC switch.
Mhm.
And I know Rita and other people, you know what I'm talking about. There are people developing real AC switch,
Right.
which is not two device back to back.
Uh-huh.
So if it's two device back to back, does the equivalent resistance or the losses is the same as if you have an unfolding bridge versus AC switch configuration. It's the same number of devices and same losses. It just
Mhm.
putting them in different places. So the game changer, of course, if you have a real AC switch, then of course you will go with you don't need an unfolding bridge anymore. Yeah,
Mhm.
that so right now it's still easier to do unfolding bridge because your gate driver, your reference design, your grounding is or more like a traditional inverter. Yeah.
Okay.
I think that equivalent, basically equivalent right now, I think.
Yeah. So, maybe one final question from my side. So, Professor Alex, as someone is, I am personally also working on SST somewhat. So, as someone trying to build, let's say, 100 kilowatt or a 200 kilowatt experimental prototype first time, what do you think is the most challenging piece of the of this puzzle? The semiconductors, the gate drivers, the magnetics. What is it? I mean, all of them are challenging, but from your own personal experience, which is the most difficult one, or the one that needs to be given most attention upfront?
Depends on the voltage, right? 100 kilowatt, if the voltage is both sides stay low, it's different, similar to traditional inverter design. And if one side has to go to very high voltage, the first thing you need to look at is that. The second one obviously is the transformer. So these are the two areas. So if it's just a 1,000 volt to 1,000 volt or 600 volt to 600 volt, on the power electronic side, I think it's more conventional design. You need to do the bus bar to minimize the losses. Then I think that then the only thing you need to worry about is your transformer, very high insulation efficient transformer design. If the one side is a couple thousand, I think that's the area most people don't have a lot of experience. I think obviously, uh, how you design your bus bar, how do you drive them to make sure your common mode noise rejection is really good, is important there. You can get a lot of false trigger, not because of the BGT, it's really the ground current, ground coupling current, your ground noise, your noise in the ground basically will get into your digital controller, can get into your gate driver. You can get into a lot of false trigger issue there. So it minimize those common mode current is very important. Everything has to be low capacitance basically. Meaning if you have isolated power supply, that power supply need to be really low capacitance. Meaning you don't want any current comes through the ground, things like that. So yeah, so those things, and I think I should pay attention. And the rest is have a guy to good at the design magnetics. Yeah.
Okay. Yeah. Thank you, Professor Alex. We've kept you 5 more minutes, I would say, more than we promised. So thank you for staying on and answering all those questions patiently. Again, as I said, you have deep domain knowledge in other areas of devices and packaging also. So we'd probably bother you sometime again in the future to pick your brains on some of those topics
When I
also.
come down to visit you, I can give another talk maybe.
Yeah, that would be excellent.
Okay.
So, let me thank you once again and the audience for again staying on and attending this webinar. And Dr. Ritu, any final thoughts from you?
No, just again, thank you, Alex. And like Shiladri said, yes, we definitely would like to have you come back and talk about a different area that you are working in. So, no, I
Sure.
really want to thank you for your time and effort, and
No
absolutely
problem.
look forward to having you here.
Okay. Take care, everybody. It's late on your
Yeah.
side. Okay. Take care.
Thank you.
Bye. Yeah.
Thank you. Thank
Yeah.
you so much. Thank you, everyone. Bye bye.
Bye bye.